Welcome, everyone. Thanks for sticking around. My name is Bill Crossley. I'm the Jürgen Vornes Head of Aeronautics and Astronautics here. I hope you enjoyed the great presentation from Bobby talking about autonomy in space exploration. So typically after the Petals lecture gives her his talk, we have a chance for some Purdue faculty members and friends to be engaged in a discussion with our guest about the topic. So we said, hey, if the autonomy is here for space exploration, where are we going to go, what are we going to do, and what are we going to find? And so that's what the panel discussion is up next. So my job now is to introduce our moderator for the panel, and then she'll introduce the panelists. Our moderator today is Nadia Numa. She's a PhD student here in Aeronautics and Astronautics, studying in our Astrodynamics and Space Applications area with Professor Kathleen Howell. So Nadia, please come on up.
Hi, good afternoon, everybody. Thank you so much for being here. It's warm, but you get to be with us on this warm day, so I appreciate you sacrificing a little bit. Thank you, Dr. Crossley, for the introduction. So I'll get us started by introducing our panelists. Dr. Robert Braun, as you've heard from, but just to remind you, he's the head of the space exploration sector at Johns Hopkins Applied Physics Laboratory. Dr. Ron Dye is our very own professor here, assistant professor in aeroastro. Her research portfolio includes autonomy for lunar rovers and entry descent landing algorithms. Dr. Kenshiro Oguri is also an assistant professor here in aeroastro. He works on robust spacecraft trajectory designs under uncertainty in challenging environments. Dr. Ben Pierce is an assistant professor in Earth, atmospheric, and planetary sciences. He studies the origin of life on Earth, as well as the search for life elsewhere in our solar system. And finally, Robert Chambers is the Future Concepts Director for Lockheed Martin's Human and Scientific Space Exploration Area. He's a Purdue AAE alumnus and a 2024 recipient of Purdue's Outstanding Aerospace Engineer Award. Let's give them a hand, please, as they come up. I don't bite, seriously.
We're in reverse order here.
Okay, sounds good. All right. Thank you guys so much again for being here. So at this time, we'll hear our panelists' opening statements, and we'll start with Mr. Chambers.
All right. Well, thanks. It's great to be back in West Lafayette. So I'm the Director of Future Concepts, which just means that I get to be the visionary for all of exploration for Lockheed. So that includes our robotic exploration missions. We've got 2 going to Venus pretty soon. Mars, Jupiter, yes, indeed. We can do solar panels. We got Juno flying around Jupiter for several years now. All the human spaceflight activities, like Orion. I was the GNC lead and flight software lead for a long time on Orion, about 100 years, it felt like, in Orion years. And as well as nuclear power and propulsion, fission, as Bobby was talking about a little ago, and then all of our earth science and weather activities. What I'm the most excited about, and we'll talk about it here, is sort of that convergence between the robotic side and the human side. You could do exploration with only one of the two, but you leave a lot on the table, and you get a lot more, exponentially speaking, when the two work together. So that'll be some of the insights I'll try to provide, is how those two to come together from an exploration perspective.
All right. Hello, everyone. Son? Yes. I'm Ben Pierce. I'm an astrobiologist. So I do experimental research from the perspective of the perhaps most fundamental questions of humankind. Where do we come from, and are we alone? And in terms of autonomy and space exploration, one area that I'm recently funded in that I find most compelling is to try and determine if there's life beyond Earth using autonomous robots that detect movement of microbes on another planet. So this is so-called agnostic biosignatures. It's composition independent. Doesn't matter what they're made of. It doesn't need to be DNA, doesn't need to be proteins, could be anything, as long as they move. Not that all life moves, but possibly life on another planet might move. And we're set out to determine whether you can distinguish living movement from non-living movement, things like Brownian motion and phase changes of water, other things that move in ways that could mimic life. So this is an area where there could be some autonomous space exploration, either in rovers bringing this technology and looking in the right places, or simply passively having these instruments on other planets, just waiting for a microbe to swim into frame. So I can provide more detail on that if anyone's interested.
Hey, hi everyone. My name is Ken Oguri. I'm assistant professor of aeroastro at Purdue University. So as a faculty member at Purdue, I've been working on astrodynamics, orbital mechanics, and spacecraft autonomy and spacecraft mission design, trajectory optimization aspects. And especially what I'm excited about this autonomy technology is, as Bobby mentioned, this enables us to explore some environments that we have never gone to, or we only have partial understanding of, especially about the dynamical systems, dynamical environments around those bodies. For example, around asteroids, we don't know the shape exactly, and that will affect the orbits and how we can predict and how we can plan our spacecraft orbital motions around asteroids or other environments. For example, on Mars, we don't know exactly what the density of the atmosphere is, and if you go to Titan, we have much more uncertainty about the dynamical environments, and then how we can incorporate those unknown or uncertainties about dynamical systems into the planning, autonomous planning, is something I'm particularly excited about, and we are trying to advance further in my research group.
Hello, everyone. I am Ran Dai, Associate Professor in the School of Aeronautics and Astronautics. My area focuses on control and optimization of autonomous systems. So one specific problem I am investigating is using autonomous rovers to explore extreme areas or previously inaccessible areas, such as lunar and Martian caves that's far away underneath the ground surface. Those areas can be used for future habitation. However, exploring those areas requires advanced autonomy and onboard decision-making, as Dr. Braun just mentioned, for the autonomous systems. Meanwhile, looking at the human-scale space missions, I'm also investigating how to land the spacecraft on a lunar and Mars surface. Precision landing requires advanced technologies combining hazard assessment in real time and also terrain relative navigation, as well as robust control technologies. And making all those technologies working in a reliable way without human interaction is a challenging mission. So these challenges will change the way how we design, test, and trust autonomous systems in the space missions.
And I'm Bobby Braun again, from the, I think you can hear me on the mic here, from the Johns Hopkins Applied Physics Lab. And you already heard how I'm so excited about the advent of autonomous systems in spaceflight. So I'll just say again, I'm grateful to be part of this panel and to be here with you all.
Fantastic. So we've heard a lot about, sort of all the different challenges and exciting developments that are coming from both of you here and also in the talk. But let's focus on one and then just kind of go deeper into it. So what's an exciting development you see coming in the next decade that will help us answer a challenge or answer a question that you're curious about that we couldn't before? And it could be from your field of expertise or your perspective as just a space enthusiast. So again, what's an exciting development you see coming that will help us answer some of these questions? Yeah, we can start with you. Yeah.
I mean, anybody can go, right? So I'll just double down on Dragonfly that I mentioned earlier, because it's launching in 2028, and you still have a chance to graduate and come work on Dragonfly at the Applied Physics Lab. I'll just mention, or elsewhere, I think Dragonfly is a remarkable will be a remarkable autonomous system. It is, it's got aeronautics in it, right? It's a space mission. It's got autonomy. Who wouldn't want to go to another ocean world? There's your astrobiology. Who wouldn't want to go to another ocean world and look for the origins of life, right? And to get to do that with a nuclear-powered car-size octocopter, it's really every engineer's dream, I think. So very excited about Dragonfly.
I can jump in. So a group of astrobiologists recently were asked by NASA to start thinking more outside of the box in terms of the search for life beyond Earth in the solar system, because exoplanets is kind of a different story in the techniques. We typically used to use a lot of chemical analysis, try and look for chiral amino acids, different chemical signatures that could be maybe a biological fingerprint, but we haven't come up with anything conclusive yet in our solar system. And there hasn't been a true purely astrobiology mission since the Viking missions led by Carl Sagan. So in this effort to try and think outside the box and develop a new technology over the next decade, we're working on more agnostic biosignatures and looking at more creative ways to try and detect life. So this came in, this idea for the so-called trail cam mission. And our idea is to place trail cams all over Mars, all over Europa, Enceladus, Titan, hundreds of trail cams just pointed at the ground or pointed inside of a cave on Mars, perhaps, that can just wait for something to swim into frame. But in order to do that, the technology we need to develop today over the next 10 years is the algorithms to distinguish living movement from non-living movement. And it's unclear whether traditional algorithms are going to be enough. This is maybe where AI and machine learning is really going to need to come in, and we can train our data set. We'll have microbes swimming in the lab here at Purdue, which will have tons of time-lapse images. Train our data set on living organisms moving, train it on abiotic movements, and see if that could perhaps be a better way to develop these algorithms so that we can finally find life beyond Earth.
I've got to. My daughter's sitting in the back. She'll like this story. I got a note from our home camera that's mounted out on the driveway, and it said like animal detected this morning, and it was my son leaving for high school to go catch the bus. So Harry set off the animal camera. So we've got it was a beta version of the trail cam. We need to do better. I'd be remiss if I didn't talk a little bit about Artemis. So the Orion spacecraft is launching in about a year. We'll send 4 humans out past the moon. And I mentioned I worked flight software on Orion for a while. So if you go way back to the dark ages, I worked on a program called EOS Terra, which is a remote sensing weather. Think of it as an environmental spacecraft at Goddard. And I was flight software dude then, and maybe we had like 500 useful telemetry points. On Orion, on Artemis 1, we had 200,000 telemetry points. On Artemis 2, where we'll fly the crew, it's probably 4 times that. We've got about 2 million lines of code in the safety critical, tested within an inch of its life flight software. So if you think about it, the way we talk about it is that we're drowning in data but starving for information. And it goes back to something that I really resonate with that Bobby said. If we can process the data out there, we can, of course, send the information back instead of the raw data to the MCC. And we were joking about making DROs great again, but we're using NRHO for the nerds in the room, which is about a 7 to 9 day orbit. Professor Howell is going to correct me, but it's around a week, let's say. And there's only so many abort times. And so my old manager, who was a shuttle astronaut, said, we have to stay and fight. So the more information, rather than raw data, we can provide these astronauts, we can then get home safely. So on Artemis 1, we flew, and this is not autonomy or AI, but we flew Alexa, which was like cool. It was my idea. If you like it, it was my idea. If you didn't like it, it was somebody else's bad idea. But it wasn't about flying, although it was fun, that wasn't about flying Alexa. It was to put in a commercial computer that could hook up, because there is no internet out there. So Alexa had to be hosted on its own platform. But we gave it access to all the telemetry in the spacecraft. And you could ask it questions, how fast am I going? When's the next burn? That was so that we could figure out how to hook up commercial processors to safety critical systems. They would not let us, Alexa abort mission, like there were some commands. They actually wouldn't let us command anything other than the lights, color lights. But that to me is what's exciting as we move forward. To answer the question finally, what I'm excited about is the ability to start using these commercial systems in conjunction with incredibly wrung out, tested, safety, mission critical systems in order to enrich the understanding by the astronauts and actually accomplish more and be safer in the process.
Yeah, so to add something to what we have discussed so far, so as Rob and Bobby both mentioned, I think the intersection synergy between different fields in engineering, outside of engineering, science, everything, different fields are getting more collaborative and then getting merging together to create something new that will enable something, some missions, ambitious missions that otherwise we cannot achieve. Is something I'm really excited about, and also I think that's something we are seeing in this current recent decades. And then from my point of view, as an astrodynamics researcher and also as a control theory researcher, I have seen lots of advance in astrodynamics point of view. For example, three-body system understanding of multi-body dynamical systems, n-body dynamical systems. For example, Professor Hauer is the top expert on that. And then we have been making progress on astrodynamics, orbital mechanics side. At the same time, I have also seen lots of advance in control theory side, which allows us to design more capable control algorithms or trajectory design optimization methods that can incorporate all the uncertainties that I mentioned earlier into the planning phase of space missions or autonomous decision-making processes on board. And then we are seeing this synergistic collaborations between those different fields, and I think this recent decades is going to be much more exciting to see those intersection and synergistic collaboration between each different fields.
I would like to add something, a new topic we are investigating. So every space launch, especially for launching large-scale infrastructure, such as large-scale solar panels and large-scale telescope, we have to put all those structures in a limited volume of firing so that we can later deploy them in space. So those deployable systems, most of the time they may require astronauts for manually deploy them. So we want to see if we use advanced autonomy technologies, can we autonomously deploy those large-scale systems? So that requires precise dynamic modeling and robust control that will control the folding and unfolding process of those deployable systems. And the benefits is, one, we will save cost in the launching and also reduce the risk for astronaut space working.
Thank you so much. So now we invite the audience to chime in. Do we have any questions?
Right. So while the autonomy is, of course, enabling like so many different concepts that were previously impossible, but is there some nuance in employing autonomy means some kind of a more risks involved in the overall architecture to some degree, like coupled with the fact that the space flights are hard to test, unlike self-driving cars, for example. So is there any kind of a overall effort to quantify the risks involved in using the autonomy to begin with, I guess? My question.
If I can talk a bit about that. Yes, that's important field of research, and then that's what I'm particularly interested in, how we can quantify those risks, and then their uncertainties, and how do we quantify, mitigate those risks, and then plan the missions that has less risk or almost zero risks. And I think that's important direction that we have to go in order to make autonomous spacecraft operations more real things in the coming decades.
Anyone else like to chime in?
From kind of a human spaceflight perspective, I mentioned there's 2 million lines of flight code. I think at peak we had 400 flight software people working there, or 400 software people total, maybe 150 flight software folks working full time. And that wasn't to sling the code, that was to test the code. Everything from unit tests to level 3, level 5, level 7, integration, all things like that. We're never going to get to the point where we can turn data into information if that's the approach we take. However, one of the things we're really careful on is don't ever give the crew bad data. So how do you balance that? How do you strike that balance? Because if you can only give the stuff you rigorously tested, it will not be artificial intelligence. It will not be machine learning. It'll just be what some software person coded in a if A, then B standpoint. Mm-hmm. So this didn't really answer your question other than everyone's worried about it, but we have to figure out how to actually go verify and validate these systems. And it's why, partly because I have both human and robotic spaceflight in my portfolio, but I really think the synergy of the two, having a human brain in the middle is still the way to turn even that information from conjecture into fact based on running a common filter across the whole universe that you're looking around inside your cockpit, if you were. It's really hard. It was a total non-answer because I don't know the answer, but we know the problem.
Can I ask a question about that? It's just a follow-up question to that. I wonder, how is risk evaluated from the perspective of also science value that could be obtained in higher risk areas? So one example could be the recurring slope lineae on Mars, these regions that may or may not have liquid water periodically would be a difficult engineering feat to get to, perhaps a lot of risk, but the potential science value might be very high. So is that also considered? This is to anyone.
Yeah, so I mean, that's a great question, actually. And I mentioned that the rovers have gone to more and more scientifically interesting places over time as autonomy has allowed. There are still large regions of Mars, including the slope lineae, that are off limits. It's interesting. Like part of the scientific community really wants to go there and explore, and then others have labeled it what's called special regions, meaning that you need very sophisticated planetary protection techniques, even like to put your robotic arm, to touch one, so to speak. And there's not consensus in the science community about risk versus reward in some of these places, because as soon as you touch something, you've obviously influenced it, and then future scientific investigations are dependent on whatever potential contamination you may have brought with you. It's also true that NASA goes through cycles of risk versus reward, where for a while they'll say, well, we're going to be risky. The Eclipse program to the moon is a great example where NASA was talking about shots on goal. As long as we get a lot of shots on goal, that's fine. But if you try to take that same level of risk with landing the Perseverance rover, which is a very unique and expensive rover, let alone humans, right? If we try to land humans on the moon in the way that we're doing with the Eclipse program, NASA wouldn't stand for that kind of risk posture. So it's somewhat a function of either dollars or the preciousness of your payload that means you can't take the risk that you would like. And it's also sometimes governed by the science community itself that wants to protect future science investigations from present science investigations. So it's a complicated set of politics there.
I guess just to pull a little bit on that. So then how do you build trust? And I think this can be from, both your industry perspective as well as your academic perspectives. So how do you build trust in that system to then autonomously do all that you're asking it to do?
Well, you do a lot of testing, that's for sure. So all of our spaceflight programs, in this country at least, all of the spaceflight programs have very sophisticated ground-based or relevant environment test programs. The rovers, for instance, on Mars, we have test beds of those systems back at JPL. When we were flying DART towards an asteroid, we had a test bed of all of the autonomous and fault protection and other compute capabilities on board. And you run those things, you run your test beds through thousands of simulations in a Monte Carlo type sense. But if we're moving towards AI, then that's no longer sufficient. And as has been mentioned already, we would need new approaches for verification and validation.
I think you just have to get over it and hail your software overlords because they're here. But the approach, so yeah, test like you fly and fly like you test, right? Is that little mantra we use. But at some point, you're limited by your imagination of the things that you can inject that in reality you didn't understand it nearly as well. What we expected at Bennu with OSIRIS-REx, which was supposed to be a sandy beach, was like this rock pile, and we plunged, shoulder deep into it. So you have to be robust and sometimes keep it simple. But I think in terms of validating these complex systems, you have to just have them ride shotgun for a while and see how they operate in application, not just on the ground. See how they operate, and then again have that human that's interacting with them, whether it's back on the ground or there, that finally just gives you the confidence. And if it saves your bacon in a couple of cases, then you gradually move its way up there. But it won't be a binary switch, and I don't think we'll ever completely be able to verify it. So I think you got to let it ride shotgun with you for a while.
And if I can add something from academic perspective, I think important thing I feel like is in order to build trust into autonomous systems, I think it's also necessary to build trust on what we develop as academia from operators. I think we need lots of conversation, discussions, collaborations, interactions between academia and industry for us, we have to explain what this algorithm can do and also what limitation this new algorithm might have. And then oftentimes there are some practical constraints that academic research may not be able to detect or identify before developing something new. So on the other hand, knowing these practical limitations, constraints can be a source of seed of innovations. Sometimes we have to develop something very new or more capable algorithms in order to handle those practical constraints, and that leads to the new innovation. So I think this synergistic collaboration between industry and academia will be probably another important factor to build trust in the system that we develop by the operators and industrial industry point of view, I think, from academic point of view.
Yeah, I would like to add in terms of validation, it also depends on can we create a testing environments as close as possible to the real space environment. For example, we tested our rover. They can work over the sanding area, but if we change the surface to similar to the lunar regnus, it's very loose and it may cause failure. The rover may get stuck on those very soft sand. So this gives us some inspiration in order to have a very effective validation, creating comprehensive testing environments as close as possible to the real space environments will be very important.
Okay, thank you. Audience, questions? Yes.
Thank you all. I was wondering if you could talk a little bit a bit more about autonomy in human spaceflight. So during the talk, we heard about probes and landers that would be fully autonomous in the future, but I was wondering if you had thoughts on whether we would ever reach fully autonomous human spaceflight and spacecraft, and whether those would ever be fully self-sufficient from Earth.
Braun?
I hope not. And kind of jokingly, the more we can offload the crew from the stuff that computers can do well, the better, and frame and focus the gray matter on the stuff that doesn't compute. No pun intended. So, for example, we talk about manual piloting or manual control of spacecraft. Completely, for any of the G and C nerds, like there's no manual control. Like you're not thruster on, thruster on, thruster on. You're doing manual guidance into some closed-loop control system, right? And that's because computers can close minus k times error equals thruster firing much better than a human can, much faster, and you have the human looking around seeing what's going wrong. I think from an autonomous perspective, the less they have to do in terms of burn planning and all those types of things, the more they can focus on the science mission. What I did learn from some of my astronaut bosses in the past, though, is there's sort of this valley of perfection, or maybe it's a mountain of perfection. So if you're really, really busy and you're actually trying to, turn every thruster on individually, you have no idea what's going on. If everything is completely automated and autonomous, then you have no idea what's going on because like everything is just fine, right? Falling asleep while you're driving on cruise control or something. So there's sort of a sweet point where you know what's going on and you've got a handle on things and you can spot it when the cockpit's not quiet and dark. But that you can have enough bandwidth that you're focusing on the science or the mission you're going to go perform. And I think that'll be the sweet spot. And then having the computer where you can just ask it, when's my burn plan coming up? That I think that's just what we do here on the planet. And so anything you use at home is exactly what we should have in human spaceflight as well.
Yeah, I'd like to see more payload specialists and fewer pilots, if you will. I could imagine that over time. If you think about the moon, like Antarctica, right? It's scientists that journey to Antarctica each season and do their scientific exploration and then come home. You could imagine doing that at the moon. I think there's all kinds of possibilities for robotic assistance of human exploration in the very near term. But I don't think it'll replace human exploration. When it gets right down to it, I mean, there's something particularly cool about, having a person there. And it's I think it's partly emotional for everyone else back here on the Earth. But it's also true that humans can adapt to all kinds of crises and take a systems view, perhaps, of something that was totally unplanned, when needed. So I think it's going to be like Rob's been describing. I think it's a mix. I don't know how many people would, if you think about like private citizens going into spaceflight pretty soon, like they're already doing it. I don't know how many people would get on a private spacecraft if it was completely autonomous, right? There are people that won't get into an autonomous car, for example. So I think the market also has a factor there. But there's no doubt that we've moved away from, the way, going back to the moon, we've definitely moved away from the Apollo era. right? We're not, even if we go back to the moon with the same number of astronauts, it's not going to be anything like the way it was in the 60s. There's going to be much more use of autonomous systems, and that extends the capability in a big way.
A running joke in the software team is the ideal crew on Orion is 2, 1 person and 1 dog. The dog is there to bite the human if the human touches the controls, and the human is there to feed the dog. And this wasn't recorded, right? Because that was actually my boss told me that joke. He's an astronaut. It's okay.
Okay. Anybody else? Question?
Hi. So, my bad. Dr. Braun, you were talking about how the Ingenuity helicopter received this sort of a software update where you send more code so that it could do more. Well, I was wondering, through automatization, how plausible would it be to do hardware modifications in the sense of like remote structure assembly? So like sending materials out there and through automatization having the structures be built remotely.
Yeah, no, it's definitely coming. And I think it's happening in Earth orbit. It'll happen in Earth orbit first because you can try things, you can experiment in Earth orbit first. There's already systems, north of Grumman has a life extension module that you can purchase today, and it'll cozy up to your spacecraft if you've run out of propellant for station keeping, for example. And it'll supply that propellant, not transfer the propellant, but just by being part of your spacecraft, it will control your orientation and those sorts of things. And I think that those kinds of capabilities will continue to advance. In situ resource utilization at the moon or on an asteroid, at Mars, I think that's definitely the way of the future. You don't necessarily have to send, tools or equipment from the Earth if you can make them with 3D printing or those types of things. And so, I think that's where we're headed.
Yeah, Dr. Dunn, I think you were talking a little bit about that in terms of solar array manufacturing and construction.
Yes, so we look at how to deploy large-scale solar arrays in the space without human interaction. So we have the dynamic model for those solar panels and also develop autonomous control as well as efficient actuation system. So far, most actuation systems rely on tethering system. We are also looking at the shape memory wires that will rely on the accurate temperature control to actuate the folding, unfolding of those deployable systems. So in the future, we are also looking at the possibility of building those solar arrays in space directly.
Picking up on that too, Dr. Oguri, could you talk a little bit about how you add autonomy in your trajectory designs, specifically in highly dynamic environments?
Not necessarily for on-orbit manufacturing or
however,
general?
Yeah.
So yes, so mathematically, so we are tackling this problem mathematically from optimization point of view. However, in essence, we want to incorporate some sense of uncertainty, and then uncertainty comes from different factors. For example, you have to do some navigation estimation of your spacecraft current position and velocity, and that's not exactly correct. You always have some errors, and also your dynamical environment, those are also uncertain. So we can model those errors, uncertain errors, by using probability, uncertainty distributions. And then we can incorporate this into trajectory optimization method, and then that will become stochastic optimization problem, stochastic optimal control problem. And then we are developing some algorithm to solve those stochastic optimal control problems in a more tractable manner. And then the hope is that we can achieve more ambitious mission. For example, there's the geyser that emits water from the surface of Enceladus. And then if we want to collect those water plume out of Enceladus geyser, we might be able to react to those observations, spontaneous observations, and make the change the course of the trajectory and then do flyby. And then those will require more autonomous decision making on board. At the same time, this has to be, we don't want to risk of, for example, impacting Enceladus for the sake of science. So we have to have some sort of those reactive autonomy at the same time ensuring the safety of those spacecraft, and then how we can mathematically, quantitatively evaluate and mitigate those risks under trajectory design or mission design perspective. That's the effort that we are working on. Does that answer your question?
Just wanted us to get a perspective as far as how you're using that in terms of the trajectory design aspect of it. Anything else from the audience? Questions? Oh, yeah.
No, well, it's kind of cheating because I helped write the title of the panel. So where do you want to go, right? If we've got autonomous capability in our spacecraft, where do you want to go outside of the Earth that we can't go today? What's really got you excited?
Anybody?
Mars. So I actually said I wasn't going to retire until we had humans at least in Mars orbit. And my wife's like, okay, we may reconsider that pledge. We've been eating our vegetables in low Earth orbit for a few decades now, right? Learn how to work, operate, build things autonomously and with human intervention. Now we're going back to the moon, and so that'll be our main course for a little while. But dessert is Mars. And there's a lot of talk. Everyone has their own idea of how to go to Mars. Should you go to the moon first? What should you do? Should you go out of Leo? Should you go out of high Earth orbit, which there's one that happens to have the moon in it. So should you go from lunar gateway? In all cases, most of us think we need to get humans into Mars orbit, and then from there decide what to do next, quite honestly. And it was funny, we put together our version, happens to be called Mars Base Camp. Came out a few years ago, and we just use that as kind of a reference concept. But I remember meeting with the planetary scientists. We've got some on staff, and then we reached out to the folks everywhere, including APL, JPL, and said, okay, what if you had big, fat, wide bandwidth, low latency in Mars orbit? How would that change how you explored the entire planet? And the answer came back, well, latency is not that big a deal because we meet once a day in the afternoon and do sort of the maneuver planning, and then we get the results the next day. So the latency doesn't, of an hour doesn't matter. And it was this epiphany. No. The reason you only meet once a day is because of the light time and the fact you're not actually doing autonomy. So let's say, and so we tried to, it didn't stick, but we were trying to, what Bobby said, scientist astronauts with a little hyphen in between, and said, okay, now you're no longer, working through a voice commanded astronaut. You are on orbit around Mars, and with the push of a button, you can deploy probe to hypersonic flight over the North Pole, drop a Ingenuity version 7.0 over here. How could that fundamentally change how quickly we could understand the red planet? And those became really, really exciting conversations. And again, I'm a broken record, but it was like the combination of humans in the vicinity and then incredibly capable autonomous systems that could be interacted with from orbit.
Yeah, so I'd like to go to the ocean worlds. So, the Earth is an ocean world. It's the only world that we know of where there's life. It takes a number of things, for that life to exist and to flourish. We know of other ocean worlds in our solar system, Titan, Enceladus. There's quite a few moons in the outer solar system that look interesting. There are ocean worlds around other stars. We know that for a fact. Imagine actually seeing one up close. Whether it's inhabited with life or not, I think just approaching an ocean world around another star would change the world, change the way we think of our very own ocean world. It's crazy and sad in a way to me that Dragonfly is the NASA's first mission to the surface of another ocean world. We should have had dozens of missions to the surface of the ocean worlds in our own solar system by now. And, as I said, I think the ocean worlds in our universe are probably, as diverse as you can imagine. So I'd like to explore quite a few of them. And autonomous systems are the way to do that.
I would say ocean worlds as well. But if I cannot choose ocean worlds, I would want to go to one of the stars like Alpha Centauri system, those kind of another star, whether we can see other life or what kind of environments they are. That's, I think I would want to go if I can go anywhere.
I would say Mars, but with sufficient resources. So I would like to go there with a very efficient logistic network that will continuously supply resources. I don't want to be starving there.
Yeah, where are you going to get pizza?
Looks like I might be the tiebreaker. I'm going to say Titan, so ocean world side, but I also want to go to Mars, so it's kind of a cheat.
For the record, Mars, we think, did have an ocean at one time. So we're all family here. It's all good.
That's true. Something that me and my graduate students are thinking about is how to increase the science value of missions that are already going on, like Dragonfly, and autonomy, the science autonomy that could be added to them. So, Dragonfly has limited sample containers for GCMS analysis. If we're trying to detect prebiotic chemistry on Titan, how do you choose your sites? Do you go to 30 different sites? Do you sample 2 at each site? You could pre-program that, but a better way would be to involve some autonomy so that when you sample a site, if it doesn't come up with something that is suggestive that there would be rich prebiotic chemistry, that you move on, and you maybe move on in a way that is intelligent. So we're thinking about different diagnostics that could be used with the GCMS to try and tip the bar to say this site is really interesting, continue to sample here, versus this site is more indicative of abiotic activity or something that you might find in meteorites, perhaps move on.
Great, thank you. Anybody else? Question? I have a question here too. Is so how do we handle like the responsibility and ethics? So if something goes wrong, we fully automated everything, and something goes wrong, who's responsible? So are we talking about that right now? Like, do we have an answer?
Oh yeah. There's quite a bit of work on like AI and ethics, for instance, or autonomous systems and ethics. There are conferences, frankly, on the topic. Mostly it focuses on, Earth-based systems, when your autonomous car runs over someone in a crosswalk, by accident, or was it intentional? That kind of thing. But there's a lot of work going on there. I think that's a great example of where, because there's so many people on the Earth, right? I think the Earthbound applications will lead space, in that regard, and in space we will, utilize what people have learned already, on the Earth. Let's say at the moon, for instance, when there's autonomous agents operating in close proximity to astronauts, much like, if you think about robotics, for instance, it used to be that if you had a factory full of robots, it wasn't that long ago, you couldn't have humans in that factory. And now, with certain kinds of robotics that have been deemed to be safe, you can go into a factory and see people and robotics, hand in hand almost. So, the robotics industry went through that kind of advancement over, in terms of safety and a little bit of ethics. And so I think in autonomous systems, the same, you'll see that same kind of evolution.
reminded me, I got to go down to JSC one time, and you guys are all familiar with Robonaut, or hopefully you are. And so you could actually go up and literally shake hands with it. And as a software guy, I'm just like freaking out. Like, there's no way. Like, who coded this, and how much money did they pay them? And it was really, I mean, I'm joking about it, but it really made me think about actually putting my hand in the grip. And it wasn't like I was shaking its hand. It was a mutual thing. It had force feedback and the whole 9 yards. And I think there's sort of this comfort level that the average human is going to have to get used to. And I think the average human doesn't really recognize how much autonomy is already going on. Like, you get into a self-driven taxi and, like, you know, everybody's Googling their family sending pictures, you know, FaceTiming or whatever you guys use, chap snatting, the family of what all you're doing. But I think until we actually start to get forced to interact with that, like, we don't even know what questions to ask about the implications of these autonomous systems that are already out there, but you haven't really seen them, you know, face to face yet.
Audience? Okay. So from an academic perspective, as well as an industry, how do you see the evolving geopolitical landscape affecting fundamental research, partnerships, and all those things? I thought that was a light one, so.
Wow.
You use the word political, so I'm out.
Geopolitical landscape. I'll jump in, and I'll just say, you know, geopolitical competition is hotter than ever, right? So the brightest minds are wanted everywhere. There are investments particularly in the areas we're talking about here, autonomous systems, AI. You know, there are huge investments being made, you know, in China, across Europe, you know, in the Middle East, frankly, not just in the U.S. So it's not like, you know, it's not like it was, you know, decades ago where, you know, you kind of knew who your competition was, and there was like one adversary, and, you know, you were kind of squaring off, and, you know, they would get ahead, then you would get ahead, and it's global. And I think, you know, people are building off of each other's advances as well. There's a lot of, whether it's planned or not, there's a lot of sharing occurring. So, yeah, I mean, I think that's the technology landscape these days. I do think that, you know, one last point I'll make, you know, most of, in the fields that we're talking about, most of the real true advances are coming from academia. They're coming from labs like APL or JPL. They're coming from actually the federal labs like, you know, Sandia or AFRL, for example. And all of those places, which are funded by the federal government, you know, are looking at restrictions these days in funding. And so, you know, I think there's a question about that and where we go as a country. But I personally think those investments are very important. And you know, I've seen some of it here in the labs, you know, at Purdue, frankly.
Yeah, I think it's a hard question, and I don't think there's a single answer for that. At the same time, as Bobby mentioned, it's very important to keep investing, I think, this fundamental research as a country or as an international community. And I think as an academia, as a professor at university, what I try to remind myself always is what might be the potential consequence of developing these new technologies or new fundamental research. Even if it's fundamental research, it might have some consequence or effect on future technologies. And then trying to be aware of those potential consequences is, I think, important from my point of view. And whenever I talk to my students, that's something I always keep in mind, what this might entail and whether that's something I am going to be comfortable with or not, and also whether the students are comfortable with that or not. Overall, I think it's very important to keep investing all those fundamental research, but I think that awareness is something everyone can, I think, keep in our mind, I think.
I'll just, I'll third that maintaining funding for fundamental research will keep America competitive in the space sector. Fundamental research is where discovery comes from that enables technologies that we can't even dream of. So we need to continue to fund this this area, and it's, I'd say, a little concerning considering potential rumors of cuts and things like this. So nothing's set in stone yet, but I would say I try to remain optimistic, and I think as the more people who speak out, we can hopefully influence the government to continue to fund NASA and other areas in space.
I'm a pretty optimistic person. So like almost everybody here, I missed the moon landing in '69. I was born after that. Been pretty bitter about it ever since. So that's why I'm working on it now. I was in D.C. last week and had a chance to talk to a variety of different congressional offices, and there are not a whole lot of things that Democrats and Republicans agree about, but space and space exploration is one. The other, I think Bobby used the word global. Exploration, like you leave the planet and it is immediately global, right? Everything you do affects everybody else, and exploration itself is far bigger than one country and far, far bigger than one company. The back end of Orion actually comes from the European Space Agency, and yes, that's in metric, and the front end of the spacecraft is in English units, and we have to work really hard to make that work. But it's because one country can no longer afford to do all this on their own. And so there's an inherent collaboration. And so I actually feel that the moon itself is a draw, and there's a lot of folks around the world interested in going to the moon and doing things at the moon. And I actually see that as a sign of optimism for collaboration. It started with the International Space Station, and we're continuing it with the Artemis Accords. I actually see sign for hope and interest that will continue to be at least one pull towards it. And if we could just set up some trail cams and find something wiggling across the regolith, that'll increase things even more quickly.
Audience, questions? There's a question here.
I just wanted to build on the previous question. Quite far-fetched, actually. It's interesting how you said ever since World War One, science and engineering have been a competition in terms of progress. What do you think would take for it to be not a competition and collaboration?
So I actually think it's both. I think in most cases it's both, right? So the Applied Physics Laboratory, APL, we compete with JPL, the Jet Propulsion Laboratory. But on Europa Clipper, we work together, and Europa Clipper wouldn't have launched without both of those labs working together. Rob's example about Orion and the Europeans, in a lot of times we're competing with the Europeans. In that case, the collaboration was required. The Europeans are actually working with JPL now on landing their next rover, which is going to Mars within a year or so. So there's a lot of collaboration that occurs. I can think back to when I was at CU Boulder just a few years ago. The Emirates had a Mars orbiter that they flew. The LASP, the Laboratory for Atmospheric and Space Physics at CU Boulder, was a big part of that mission, right? As was UC Berkeley. Sorry about that. UC Berkeley was a big part of that mission as well. So Dragonfly has people from all around the world working together on it. There's probably people at, 30 or 40 different organizations that are part of that mission. On the other hand, competition, fuels innovation. It does. Just, competition between companies in artificial intelligence here on the Earth, competition between space agencies to go farther, to go faster. It's a natural, it's part of being human is to compete.
If you were all guaranteed to get A's, how hard would you all be working?
That's a great example.
Or PhDs from Professor Howell.
Yeah. So I think the answer is going to be both, is all I'm saying.
As we wrap up here, I have one last quick question, and I promise this one's light. I saw an interview of yours where you said you wanted to be a fireman and then a brain surgeon when you grew up. So I'm just kind of curious for the panel, what would you do if you weren't doing this? And you can start.
Fireman and brain surgeon, because that's what I've said officially on the record. Yeah, probably brain surgery, just because it sounded really, really hard. That sounds really, really hard.
It's tough because I would need to keep my brain stimulated, and science does that for me. On the other hand, I have a lot of passion for fitness and health and lifting, so I might just be a personal trainer. Try and advance and see how I could build more muscle faster.
I think you were going to say game warden. Trail cams, game warden, out in the nature, maybe?
Yeah. That's a good one.
It's a tough one. I think I would want to be still in academia, but planetary scientist or astrophysicist, if it's an acceptable answer. And I want to, in any role, I want to pursue space exploration, space expansion as a humanity. So that's my answer.
Space, true and true. Got it.
There's something I really want to do is having my own startup. I'm thinking making robots. They will do the hair and makeup autonomously. So I don't need to do those things.
That's a great idea. That would be good. I went to school originally to be an architect. And so that was my plan all through high school and into college. And then I got to college, and it was just not for me, the architect part. And fortunately, aerospace is very close. Architectural engineering and aerospace engineering are alphabetically very close to each other. So the transfer worked out just fine, and I didn't lose much time. I think prior to that, I was in a band, so I might go back to that one day. Rhythm guitar.
Braun and the Friends, or what are we?
Well, we were kind of a cover band, teen club, stuff like that. We got paid, I think, 3 times. So it wasn't that much of a band, but it was fun.
They're putting the band back together. Can you join me in thanking our panelists and our hosts today? Nadia Numa, Bob Chambers, Glenn Pierce, Glenn O'Gurry, Ron Dye, and of course, Bobby Braun. Thank you very much. Thanks for coming this afternoon. Thank you.